Okay, this is lecture 12. We've reached 12 lectures, and this one is more than the others about applications of linear algebra. And I'll confess, when I'm giving you examples of the null space and the row space, I create a little matrix. You probably see that I just invent that matrix as I'm going. And I feel a little guilty about it, because the truth is that real linear algebra uses matrices that come from somewhere. They're not just like randomly invented by the instructor. They come from applications. They have a definite structure, and anybody who works with them uses that structure. I'll just report, like this weekend I was at an event with chemistry professors. Okay, those guys are row-reducing matrices, and what matrices are they working with? Well, their little matrices tell them how much of each element goes into the, or each molecule, how many molecules of each go into a reaction and what comes out. And by row reduction, they get a clearer picture of a complicated reaction. And this weekend, I'm going to a sort of birthday party at MathWorks. So MathWorks is out Route 9 in Natick. That's where MATLAB is created. It's a very, very successful software, tremendously successful. And the conference will be about how linear algebra is used. And so I feel better today to talk about what I think is the most important model in applied math. And the discrete version is a graph. So can I draw a graph, write down the matrix that's associated with it, and that's a great source of matrices. You'll see. So a graph is just, so a graph, to repeat, has nodes and edges. Okay, and I'm going to write down the graph, a graph. So I'm just creating a small graph here. As I mentioned last time, we would be very interested in the graph of all websites, or the graph of all telephones, or the graph of all people in the world. Here, let me take just maybe nodes 1, 2, 3. Well, I better put in I'll put in that edge, and maybe an edge to a node 4, and another edge to node 4. How's that? So there's a graph with 4 nodes. So n will be 4 in my n equal 4 nodes. And the matrix will have m equal the number. There will be a row for every edge. So I've got 1, 2, 3, 4, 5 edges. So that will be the number of rows. And I have to write down the matrix that I want to study. I need to give a direction to every edge. So I know a plus and a minus direction. So I just do that with an arrow. Say from 1 to 2, 1 to 3, 2 to 3, 1 to 4, 3 to 4. That just tells me if I have current flowing on these edges, then I know whether it's to count it as positive or negative according to whether it's with the arrow or against the arrow. But I just drew those arrows arbitrarily. Okay, because my example is going to come, the words that I will use will be words like potential, potential difference, currents. In other words, I'm thinking of an electrical network. But that's just one possibility. My applied math class builds on this example. It could be a hydraulic network. So we could be doing flow of water, flow of oil, Other examples, this could be a structure, like a design for a bridge or a design for a Buckminster-Fuller dome, or many other possibilities. So many. So, but let's take potentials and currents as a basic example, and let me create the matrix that tells you exactly what the graph tells you. So now I'll call it the incidence matrix. Incidence matrix. Okay. So let me write it down, and you'll see what its properties are. So every row corresponds to an edge. I have 5 rows from 5 edges, and let me write down again what this graph looks like. Okay, the first edge, edge 1, goes from node 1 to 2. So I'm going to put in a -1 and a +1 in, this corresponds to node 1, 2, 3, and 4, the 4 columns. The 5 rows correspond, the first row corresponds to edge 1. Edge 1 leaves node 1 and goes into node 2, and it doesn't touch 3 and 4. Edge 2. Edge 2 goes, oh, I haven't numbered these edges. I just figured that was probably edge 1, but I didn't say so. Let me take that to be edge 1. Let me take this to be edge 2. Let me take this to be edge 3. This is edge 4. Oh, I'm discovering, no, wait a minute. Did I number that twice? Here's edge 4, and here's edge 5. Okay? All right. So edge 1, as I said, goes from node 1 to 2. Edge 2 goes from 2 to 3, node 2 to 3, so -1 and 1 in the second and third columns. Edge 3 goes from 1 to 3. I'm tempted to stop for a moment with those 3 edges. Edges 1, 2, 3. Those form what do you call the subgraph formed by edges 1, 2, and 3. That's a loop. And the number of loops and the position of the loops will be crucial. Okay. Actually, here's an interesting point about loops. If I look at those rows corresponding to edges 1, 2, 3, and these guys made a loop, you want to tell me, if I just looked at that much of the matrix, it would be natural for me to ask, are those rows independent? Are the rows independent? And can you tell from looking at that if they are or are not independent? Do you see a relation between those 3 rows? Yes. If I add that row to that row, I get this row. So that's like a hint here that loops correspond to linearly dependent linearly dependent rows. Okay, let me complete the incidence matrix. Number 4, edge 4 is going from node 1 to node 4. And the 5th edge is going from node 3 to node 4. Okay, there's my matrix. It came from the 5 edges and the 4 nodes. And if I had a big graph, I'd have a big matrix. And what questions do I ask about matrices? Here's the review now. There's a matrix that comes from somewhere. If it was a big graph, it would be a large matrix, but a lot of zeros, right? Because every row only has 2 non-zeros. So it's a very sparse matrix. The number of non-zeros is exactly 2 times 5. It's 2m. Every row only has 2 non-zeros, and that's with a lot of structure. And that was the point I wanted to begin with, that graphs, that real graphs from real matrices, from genuine problems, have structure. Okay. We can ask, and because of the structure, we can answer the main questions about matrices. So first question, what about the null space? So what am I asking? If I ask you for the null space of that matrix, I'm asking you if I'm looking at the columns of the matrix, 4 columns, and I'm asking you, are those columns independent? If the columns are independent, then what's in the null space? Only the 0 vector, right? The null space tells us what combinations of the columns. It tells us how to combine columns to get 0. And is there anything in the null space of this matrix other than just the 0 vector? In other words, are those 4 columns independent or dependent? Okay. So that's our question. Let me. I don't know if you see the answer. Whether there's let's see. I guess we could do it properly. We could solve AX equals 0. So let me solve AX equals 0 to find the null space. Okay, what's AX? Can I put X in here in little letters? X1, X2, X3, X4. It's got 4 columns. AX now is that matrix times X. And what do I get for AX? If the camera can keep that matrix multiplication there, I'll put the answer here. AX equal, what's the first component of AX? Can you take that first row, minus 1, 1, 0, 0, and multiply by the x, and of course you get x2 minus x1. The second row, I get x3 minus x2. From the third row, I get x3 minus x1. From the fourth row, I get x4 minus x1. And from the fifth row, I get x4 minus x3. And I want to know, when is the thing 0? This is my equation, AX equals 0. Notice what that matrix A is doing. We've created a matrix that computes the differences across every edge. The differences in potential. Let me even begin to give this interpretation. I'm going to think of this vector x, which is x1, x2, x3, x4, as the potentials at the nodes. So I'm introducing a word, potentials at the nodes. And now if I multiply by A, I get these 5 components, x2 minus x1, etc. And what are they? They're potential differences. That's what A computes. If I have potentials at the nodes and I multiply by A, it gives me the potential differences, the differences in potential across the edges. Okay. When are those differences all 0? So I'm looking for the null space. Of course, if all the x's are 0, then I get 0. That just tells me, of course, there's 0 vectors in the null space. But there's more in the null space. Those columns of A are dependent, right? Because I can find solutions to that equation. Tell me the null space. Tell me one vector in the null space. So tell me an x. It's got 4 components, and it makes that thing 0. So what's a good x to do that? 1, 1, 1, 1. Constant potential. If the potentials are constant, then all the potential differences are 0, and that x is in the null space. What else is in the null space? Yeah, let me ask you just always, give me a basis for the null space. A basis for the null space will be just that. That's it. That's a basis for the null space. The null space is actually one-dimensional, and it's the line of all vectors through that one. So there's a basis for it, and here's the whole null space. Any multiple of 1, 1, 1, 1, it's the whole line in four-dimensional space. Do you see that that's the null space? So the dimension of the null space of A is 1. And there's a basis for it, and there's everything that's in it. Good. And what does that mean physically? I mean, what does that mean in the application, that guy in the null space? It means that the potentials can only be determined up to a constant. Potential differences are what make current flow. That's what makes things happen. It's these potential differences that will make something move in our network between node 2 and node 1. Nothing will move if all potentials are the same. If all potentials are C, 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 and C, then nothing will move. So we have this one parameter, this arbitrary constant that raises or drops all the potentials. It's like ranking football teams, whatever. We have there's a constant, or looking at temperatures. You know, there's a flow of heat from higher temperature to lower temperature. If temperatures are equal, there's no flow, and therefore we can measure temperatures by Celsius, or we can start at absolute 0. And that it's the same arbitrary constant that was there in calculus. In calculus, right, when you took the integral, the indefinite integral, there was a plus c. And you had to set a starting point to know what that c was. So here what often happens is we fix one of the potentials like the last one. So a typical thing would be to ground that node, to set its potential at 0. And if we do that, if we fix that potential so it's not unknown anymore, then that column disappears, and we have 3 columns, and those 3 columns are independent. So I'll leave the column in there, but we'll remember that grounding a node is the way to get it out. And grounding a node is the way to setting a potential to 0 tells us the base for all potentials. Then we can compute the others. Okay, but now I've talked enough to ask what the rank of the matrix is. What's the rank then? The rank of the matrix, so we have a 5 by 4 matrix. We've located its null space, one-dimensional. How many independent columns do we have? What's the rank? It's 3. And the first 3 columns, or actually any 3 columns, will be independent. Any 3 potentials are independent good variables. The 4th potential is not, we need to set, and typically we ground that node. Okay, rank is 3. Rank equals 3. Okay. Let's see, do I want to ask you about the column space? The column space is all combinations of those columns. I could say more about it, and I will. Let me go to the null space of A transpose, because the equation A transpose y equals 0 is probably the most fundamental equation of applied mathematics. Let's talk about that. That deserves our attention. A transpose y equals 0. Let me put it on here. Okay. So A transpose y equals 0. So now I'm finding the null space of A transpose. Oh, and if I ask you its dimension, you could tell me what it is. What's the dimension of the null space of A transpose? We now know enough to answer that question. What's the general formula for the dimension of the null space of A transpose? A transpose, let me even write out A transpose. This A transpose will be n by m, right? N by m. In this case, it'll be 4 by 5. Those columns will become rows. Minus 1, 0, minus 1, minus 1, 0 is now the first row. The second row of the matrix, 1, minus 1, and 3 zeros. The third column now becomes the third row, 0, 1, 1, 0, minus 1. And the fourth column becomes the fourth row. Okay, good. There's A transpose. That multiplies y. y1, y2, y3, y4, and y5. Okay, now you've had time to think about this question. What's the dimension of the null space? If I set all those, wow. Usually, sometime during this semester, I'll drop one of these erasers behind there. That's a great moment. There's no recovery. There's centuries of erasers are back there. Okay. Okay, what's the dimension of the null space? Give me the general formula first in terms of R and M and N. This is like crucial. We struggled to decide what dimension meant, and then we figured out what it equaled for an M by N matrix of rank R, and the answer was M minus R, right? There are M equal 5 components, M equal 5 columns of A transpose, and R of those columns are pivot columns because it'll have R pivots, it has rank R, and M minus R are the free ones now for A transpose, so that's 5 minus 3, so that's 2. And I would like to find this null space. I know its dimension. Now I want to find out a basis for it. And I want to understand what this equation is. So let me say what A transpose Y actually represents. Why I'm interested in that equation. Yeah, I'll put it down with those old erasers and continue this. Here's the great picture of applied mathematics. So let me complete that. There's a matrix that I'll call C that connects potential differences to currents. So I'll call these are currents on the edges. Y1, Y2, Y3, Y4, and Y5. Those are currents on the edges. And this relation between current and potential difference is Ohm's law. This here is Ohm's law. Ohm's law says that the current on an edge is some number times the potential drop. And that number is the conductance of the edge, 1 over the resistance. This is the old current is the relation of current, resistance, and change in potential. So it's a change in potential that makes some current happen, and it's Ohm's law that says how much current happens. Okay, and then the final step of this framework is the equation A transpose Y equals 0. And that's, what is that saying? It has a famous name. It's Kirchhoff's current law, KCL. Kirchhoff's current law, A transpose Y equals 0. So that when I'm solving, when I go back up with this blackboard and solve A transpose Y equals 0, it's this pattern of that I want you to see. That we had rectangular matrices and real applications. But in those real applications comes A and A transpose. So our 4 subspaces are exactly the right things to know about. All right, let's know about that null space of A transpose. Wait a minute, where did it go? Here it is. Okay. Okay. Null space of A transpose. We know what its dimension should be. Let's find out. Tell me a vector in it. Tell me, now, so what am I asking you? I'm asking you for 5 currents that satisfy Kirchhoff's current law. So we better understand what that law says. That law, A transpose Y equals 0. What does that say? Say in the first row of A transpose, that says, so the first row of A transpose says minus Y1 minus Y3 minus Y4 is 0. Where did that equation come from? I'll redraw the graph. Can I redraw the graph here so that maybe here, so that we see again there was node 1, node 2, node 3, node 4 was off here. That was our graph. We had currents on those. We had a current Y1 going there. We had a current what are those edge numbers? Y4 here and Y3 here. And then a Y2 and a Y5. I'm just copying what was on the other board so it's convenient to see it. What is this equation telling me? This first equation of Kirchhoff's current law. What does that mean for that graph? Well, I see Y1, Y3, and Y4 as the currents leaving node 1. So sure enough, the first equation refers to node 1, and what does it say? It says that the net flow is 0. That equation, A transpose Y, Kirchhoff's current law, is a balance equation, a conservation law. Physicists be overjoyed by this stuff. It says that in equals out. And in this case, the 3 arrows are all going out, so it says Y1, Y3, and Y4 add to 0. Let's take the next one. The second row is Y1 minus Y2. And that's all that's in that row. And that must have something to do with node 2. And sure enough, it says Y1 equals Y2, current in equals current out. The third one, Y2 plus Y3 minus Y5 equals 0. That's certainly be what's up at the third node. Y2 coming in, Y3 coming in, Y5 going out, has to balance. And finally, Y4 plus Y5 equals 0 says that at this node, Y4 plus Y5, the total flow is 0. We don't, charge doesn't accumulate at the nodes. it travels around. Okay. Now give me, I come back now to the linear algebra question. What's a vector y that solves these equations? Can I figure out what the null space is for this matrix, A transpose, by looking at the graph? I'm happy if I don't have to do elimination. I can do elimination. We know how to find a null space basis. We can do elimination on this matrix, and we'll get it into a good reduced row echelon form, and the special solutions will pop right out. But I would like to even to do it without that. Let me just ask you first, if I did elimination on that matrix, what would the last row become? What would the last row, if I do elimination on that matrix, the last row of R will be all zeros, right? Why? Because the rank is 3. We're only going to have 3 pivots, and the fourth row will be all zeros when we eliminate. So elimination will tell us what we spotted earlier. What's the null space? All the information. What are the dependencies? We'll find those by elimination. But here, in a real example, we can find them by thinking. Okay. Again, my question is, what is a solution y? How could current travel around this network without collecting any charge at the nodes? Tell me a y. Okay. So a basis for the null space of A transpose. How many vectors am I looking for? 2. It's a 2-dimensional space. My basis should have 2 vectors in it. Give me 1. One set of currents. Suppose, let me start it. Let me start with y1 as 1. Okay, so 1 unit of 1 amp travels on edge 1 with the arrow. Okay, then what? What is y2? It's 1 also, right? And of course, what you did was solve Kirchhoff's current law quickly in the second equation. Okay, now we've got 1 amp leaving node 1, coming around to node 3. What shall we do now? Well, what shall I take for y3, in other words? Well, I've got a choice, but why not make it, what you said, -1? So I have just sent current 1 amp around that loop. What shall y4 and y5 be in this case? We could take them to be 0. This satisfies Kirchhoff's current law. We could check it patiently, that minus y1 minus y3 gives 0. We know y1 is y2. The other is y4 plus y5 is certainly 0. Any current around a loop satisfies the current law. Okay, now you know how to get another one. Take current around this loop. So now let y3 be 1, y5 be 1, and y4 be -1. And so we have the first basis vector sent current around that loop. The second basis vector sends current around that loop. And those are independent. And I've got 2 solutions, 2 vectors in the null space of A transpose, 2 solutions to Kirchhoff's current law. Of course, you would say, what about sending current around the big loop? What about that vector? 1 for y1, 1 for y2, nothing on y3, 1 for y5, and -1 for y4. What about that? Is that in the null space of A transpose? Sure. So why don't we now have a third vector in the basis? Because it's not independent, right? It's not independent. This vector is the sum of those two. If I send current around that and around that, then on this edge y3 it's going to cancel out, and I'll have altogether current around the whole, the outside loop. That's what this one is, but it's a combination of those two. You see that I've now I've identified the null space of A transpose, but more than that, we've solved Kirchhoff's current law and understood it in terms of the network. Okay, so that's the null space of A transpose. I guess there's always one more space to ask you about. Let's see, I guess I need the row space of A, the column space of A transpose. So what's its dimension? Yep. What's the dimension of the row space of A? If I look at the original A, it had 5 rows. How many were independent? So I guess I'm asking you the rank again, right? And the answer is 3, right? 3 independent rows. When I transpose it, there's 3 independent columns. Are those columns independent, those 3? The first 3 columns, are they the pivot columns of the matrix? No. Those 3 columns are not independent. In fact, this tells me a relation between them. There's a vector in the null space that says the first column plus the second column equals the third column. They're not independent because they come from a loop. So the pivot columns of this matrix will be the first, the second, not the third, but the fourth. Columns 1, 2, and 4 are okay. Where are they? Those are the columns of A transpose. Those correspond to edges. So there's edge 1, there's edge 2, and there's edge 4. So that's like, that is a smaller graph. If I just look at the part of the graph that I've used with thick edges, it has the same 4 nodes. It only has 3 edges. And those edges correspond to the independent guys. And in the graph, those 3 edges have no loop, right? The independent ones are the ones that don't have a loop. All the dependencies came from loops. They were the things in the null space of A transpose. If I take 3 pivot columns, there are no dependencies among them, and they form a graph without a loop. And I just want to ask you, what's the name for a graph without a loop? So a graph without a loop has got not very many edges, right? I've got 4 nodes, and it only has 3 edges. And if I put another edge in, I would have a loop. So it's this graph with no loops, and it's the one where the rows of A are independent. And what's a graph called that has no loops? It's called a tree. So a tree is the name for a graph with no loops. And just to take one last step here, using our formula for dimension. Let's look once at this formula. The dimension of the null space of A transpose is M minus R. Okay. This is the number of loops. Number of independent loops. M is the number of edges. And what is R? What is R for our, we have to remember way back, the rank came from looking at the columns of our matrix. So what's the rank? Let's just remember. Rank was, you remember there was one, we had a one-dimensional null, the rank was n minus 1. That's what I'm struggling to say. Because there were n columns coming from the n nodes, so it's minus the number of nodes minus 1. Because of that that 1, 1, 1, 1 vector in the null space, the columns were not independent. There was one dependency, so we needed n minus 1. This is a great formula. This is like the first. Shall I write it slightly differently? The number of edges. Let me put things. Have I got it right? Number of edges is m. The number is m minus r. Okay, so I'm getting. Let me put the number of nodes on the other side. So the number of nodes. I'll move that to the other side. Minus the number of edges, plus the number of loops, is, I have minus 1 is 1. The number of nodes minus the number of edges plus the number of loops is 1. These are like zero-dimensional guys. They're the points on the graph. The edges are like one-dimensional things. They connect nodes. The loops are like two-dimensional things. They have like an area. And this count works for every graph. And it's known as Euler's formula. We see Euler again. That guy never stopped. Okay. And can we just check? So what am I saying? I'm saying that linear algebra proves Euler's formula. Euler's formula is this great topology fact about any graph. Let me draw another graph. Let me draw a graph with more edges and loops. Let me put in lots of, okay. I just drew a graph there. So what are the quantities in that formula? How many nodes have I got? Looks like 5. How many edges have I got? 1, 2, 3, 4, 5, 6, 7. How many loops have I got? 1, 2, 3. And Euler's right. I always get 1. This formula is extremely useful in understanding the relation of these quantities, the number of nodes, the number of edges, and the number of loops. Okay. Just complete this lecture by completing this picture, this cycle. So let me come to the so this expresses the equations of applied math. This, let me call these potential differences, say, E. So E is AX. That's the equation for this step. The currents come from the potential differences. Y is CE. The currents satisfy Kirchhoff's current law. Those are the equations with no source terms. Those are the equations of electrical circuits, of many, those are like the most basic 3 equations. Applied math comes in this structure. The only thing I haven't got yet in the picture is an outside source to make something happen. I could add a current source here. I could add external currents going in and out of nodes. I could add batteries in the edges. Those are 2 two ways. If I add batteries in the edges, they come into here. Let me add current sources. If I add current sources, those come in here. So there's where current sources go, because the F is like a current coming from outside. So we have our edges, we have our graph, and then I send 1 amp into this node and out of this node, and that gives me a right-hand side in Kirchhoff's current law. And to complete the lecture, I'm just going to put these three equations together. So I start with x, my unknown. I multiply by A. That gives me the potential differences. That was our matrix A that the whole thing started with. I multiply by C. Those are the physical constants in Ohm's law. Now I have Y. I multiply Y by A transpose. And now I have F. So there's the whole thing. There's the basic equation of applied math, coming from these three steps, in which the last step is this balance equation. There's always a balance equation to look for. These are when I say the most basic equations of applied mathematics, I should say in equilibrium. Time isn't in this problem. Newton's law isn't acting here. I'm looking at the equations when everything is settled down. How do the currents distribute in the network? And of course, there are big codes to solve this is the basic problem of numerical linear algebra for systems of equations, because that's how they come. And my final question, what can you tell me about this matrix A transpose CA? Or even A transpose A? I'll just close with that question. What do you know about the matrix A transpose A? It is always symmetric. Right. Okay, thanks. So I'll see you Wednesday for a full review of these chapters, and Friday you get to tell me. Thanks.